Welcome to today's seminar. We have those here at ISTC and also to those listening online. My name is Nancy Holm. I'm the seminar organizer. This is the second in a series of talks this semester on sustainable electronics. The next talk will be on October 3rd, again at noontime in our seminar series. A copy of the schedule for the semester and other information about ISTC and our Sustainable Electronics Initiative are on the table here for those in attendance. Others who are listening, I will put your emails on my email list and will be sending you information about future seminars and other events. Today we're very pleased to have with us as our speaker Dr. Kelly Babbitt of the Golisano Institute of Sustainability at Rochester Institute of Technology. Dr. Babbitt has been at RIT since 2009. She received her BS in Chemical Engineering from Georgia Institute of Technology. She received her ME in Environmental Engineering from the University of Florida and completed her research there on production, disposal, beneficial use of coal combustion products in Florida. Her PhD work was also from the University of Florida in Environmental Engineering, and she received that degree in 2007. Her RIT research group focuses on developing and applying tools to understand and manage the life cycle implications of emerging technologies. Specific focal areas are consumer electronics, nanomaterials, photovoltaics, and lithium-ion batteries. Today, Dr. Babbitt will discuss her work on adapting ecological models for linking sustainable production and consumption dynamics in consumer electronic product systems. I would ask those here in attendance to hold their questions to the end of the talk, and also for those listening online, you can send in your questions and then we will answer those also at the end of the talk. So with that, now we'll switch to New York and Dr. Babbitt.
Hi, thank you all for having me today, especially the ability to use electronics, which of course is the focus of my research, to minimize environmental emissions rather than creating new ones by avoiding having travel. We're sort of in the middle of our quarter here as well, and so it's great to connect with you all electronically, although I wish I was there in person as well. I'll be talking about some research today that is been the subject of a student of mine and my work over the last few years, and is the topic of a recently funded National Science Foundation grant, and so some of the work is just getting underway. So we'll be talking a little bit of a mix of some existing findings and methods and some new things that we thought might be interesting to this particular community. I've enjoyed participating with Sustainable Electronics Initiative in the past and getting to see some of the exciting things that you all are doing, and I hope that this is interesting and beneficial to some of you all as well. And there's a picture up there, so you can pretend that I'm up there on the screen as well as coming through by the computer. One quick word about our program here at RIT. We have a graduate-only program here in sustainability with degrees leading to a PhD in sustainability, a Master's of Science in Sustainable Systems, and just started last year a Master's of Architecture with a focus in sustainability. So we're trying to really stay at the cutting edge of degrees and education in this area. We also do a lot of work with industry. We work a lot with our campus sustainability officers in greening the RIT campus, and have partnered with a number of international organizations, both in terms of education and outreach as well as research. So if from this conversation today, in addition to research questions, if there is any interest in ongoing dialogue about sustainability education, that's another major interest of mine, and I'd love to talk with folks further about that. We're also very excited here to be moving into a new sustainability building the end of this year, and hope that if some of you all have a chance to come to Rochester, you'll have a chance to come see this facility, which is really going to showcase a lot of sustainable energy technologies, smart microgrid, being able to run off of the independent of the campus grid, some really exciting things. So we'd love to have any of you all come visit Rochester, maybe not in the winter, maybe in the beautiful springtime or summer next year, but we'd love to have you come visit. Getting into the research talk that I'll be speaking about today, I wanted to quickly make a mention of the sustainability challenges of electronics. Now, I know that this audience in particular is well aware of the fact that electronic products, consumer electronics specifically, create a number of environmental impacts across their life cycle, from the scarce and environmentally impactful materials used in their production, the high energy and material intensity of many of the components like silicon wafers, circuit boards, etc., along their manufacturing side, the energy use during their actual use by consumers, as well as the compounding factors of decreasing lifespan and an increase in sort of throwaway mentality. And then, of course, we all are well familiar with the challenges in end-of-life management of these materials, particularly that we have some technological challenges to making this a very high efficiency process, and so as a result many of these materials are exported, and which can cause a number of challenging social, environmental, and economic issues. So I won't get into any detail here because I'm sure that many of you all are very familiar with this, but suffice it to say that research for the last number of years has really been looking at ways to solve all of these challenges in an integrated and environmentally sustainable way. And we've come up with some really great solution areas. We certainly are seeing a lot of work being done through the EPA, for example, Design for Environment, Energy Star, etc. We use a lot of tools like life cycle assessment, in which we look at the full life cycle of the product and understand that. We have a number of labeling initiatives like EPEAT that look at designing and procuring more sustainable products. And as you know, in Illinois, which is a real leader in this area, as well as a number of other states, and in Europe, we have a number of electronics or WEEE regulations that have been put in place to try to manage these materials at the end of life. So there's been a lot of work done trying to improve the sustainability of electronics. And overall, these initiatives have been extremely successful at reducing the environmental impact per product. So an individual laptop over time is getting greener, for example, or our individual system of collecting recycling, we're getting better at that and more able to manage that material efficiently. However, the challenge is that we're continuing to consume an increasing amount of these materials, and as a result, we have observed what we like to term the rebound effect, or the fact that the efficiency gains are never able to keep up with the increase in consumption. And as a result of the fact that people don't just own one laptop, they own a complex mix of products, including televisions, desktop computers, game systems, phones, cameras, etc. And so this approach we've used in the past, which is just to take a single product at a time and try to make it greener, is not really appropriate or is limited in its efficacy in terms of dealing with products that don't occur individually, but they occur in this complex mix of products. So if we want to think about ways of addressing this challenge, we can look at the field of industrial ecology for inspiration. This is, in fact, the field that many of these existing solutions come from, like life cycle assessment, energy flow analysis, industrial symbiosis, design for the environment, etc. So if we look at industrial ecology, this field uses the idea of nature, or our natural earth, as an inspiration or model for how to green our industrial systems. So for example, in a natural system, we have a closed loop cycling of energy and resources where, say, the waste from one organism becomes the food for the next organism. And so this provides a lot of inspiration on how we can design greener industrial systems. So the inspiration for this particular research is looking at industrial ecology and asking the question, from an ecological perspective, how would an ecologist investigate, in a biological sense, complex communities of interacting organisms? If we know that, then we can think about how an industrial ecologist can investigate complex product communities like consumer electronics. And so that's really the motivation of this product is, I always like to say, what would an ecologist do? If we're going to use this idea of industrial ecology, how can we really use it to think about communities of products? And in fact, in biological ecology, we see the field of community ecology. And so the image here on the screen shows a Adirondack community here in New York in which you have a predator like a wolf who preys on deer or beavers, and so there's a negative sign indicating that the presence of that wolf suppresses or negatively impacts those populations. And then there's other organisms there like the duck who benefits from the presence of the beaver and their role in engineering the waterways. So this group of organisms lives together in this spatially and temporally defined community. They consume certain amounts of materials and resources. They consume energy. They generate biomass. And all of those flows, those material and energy flows, are governed by how many of the different organisms are there, as well as a number of external factors like environmental stress or evolution or resource scarcity. And as a result of all of these processes happening in this community, you see certain trends begin to emerge. For example, an ecologist might study the biodiversity of the system and thinking about the fact that the higher biodiversity might mean a more stable or sustainable system. Okay, so using this as our inspiration, we then want to see if we can apply this concept to consumer electronics. So instead of looking at these organisms in the Adirondacks, we want to look at the electronic products in the community that we might consider to be the U.S. average household. And so if we look at this system, we see a lot of interesting parallels. For example, we have this very complex mix of products that interact with each other. For example, owning a laptop computer might make you more likely to own a printer, so there's a positive relationship there. But it might make you less likely to own a cathode ray tube monitor or desktop computer, so a negative relationship there. Now these plus and minus signs signifying this positive or negative relationship, these are conjecture at this point. We haven't got to that stage in the research, but it's sort of a logical way of thinking about how these products interact. And depending on which products are there and how many of them the average consumer owns, that means that there's a certain amount of material flowing into the system through the materials contained in the products themselves, and then there's a certain amount of energy consumed when we as consumers use this. Resultingly, there's a certain amount of waste that's also generated. Not only is this structure dictated by the presence or absence of these products, but also by a number of external factors like regulations and voluntary standards like EPEAT, or prices of products or technologies. So this graph shows to a large extent the real conceptual framework of this research effort. The idea that we can begin to take apart dissect really this community and try to understand different ways of interpreting it rather than just looking at each product in isolation. An ecologist would never look at a single organism in isolation, so we're going to try to avoid doing that as well. So there's really three subtopics or sub-research areas that fall under this idea of community ecology for products. The first one has to do with simply understanding the structure and the diversity of the system. So trying to figure out what are the trends in consumption, which products dominate the household ownership of consumer electronics, and more importantly, taking a step back from the products and also looking at the functions they provide. Which are the functions that people demand, and how can we use that information? The next step is really focusing on the community level energy flows. So instead of applying a life cycle assessment to a single product, instead we want to try to apply life cycle assessment to the entire community of products and try to understand how the outcomes would change, specifically when we think about policy relevant outcomes or design relevant outcomes. How would we change our prioritization of sustainability improvements given this focus of the community? And finally, we want to try to understand how the structure of the community and this knowledge about which products we own will dictate what materials are consumed and also what waste is generated. We know that our current end-of-life management of products is governed by heuristics and design principles that really looked at products several years ago, looking at a lot of larger products like CRTs or desktop computers, in which we prioritize being able to disassemble these products. Maybe that doesn't make sense anymore if our community of products is moving more towards smaller, lighter, lower value electronics like smartphones and tablets. So understanding how the community structure impacts the end-of-life priorities. So these are really the three thrusts in our research topic, and I'm going to spend most of the time today talking about the first, since this is really the focus of the work that we've done over the last year. The other two are at very preliminary stages. So I'll speak a little bit about the approach there, but I'm not going to spend as much time explaining those because we're still developing those methods. So first, when we want to think about community structure and diversity, we really need to define what these terminologies that we would encounter in ecology, what they would translate to in industry. So when we think about a community in an ecological sense, we're thinking about systems like the Adirondacks, spatial and temporal boundaries. So in the same way, in our electronic system, we're going to call our community all of the consumer electronics owned by an average U.S. household from 1990 to 2010. Now, of course, these results don't represent every household, but we're taking an average to simplify the system somewhat. What an ecologist would call a species, we're going to translate that as product category. So, for example, a smartphone might be a species, not a Motorola smartphone or a Samsung smartphone. Those are individuals within the species. So smartphone being the entire product category. We also want to think about function. And there's a number of different ways to define function, but the two I'm going to talk about today are primary and secondary. Primary function being the reason that you bought the device. So the reason primarily that you would buy a smartphone would be for voice communication. Secondary function being all of the other things that come along with it. So when you buy a smartphone, you not only can talk, I think people still do that, you can also play games, email, play videos, post things on YouTube, respond to tweets, converse, etc. So it provides you a lot of additional functionality, and we want to try to assess both. The next step, once we have sort of mapped out and defined what each of these components of our community are, is to think about what an ecologist might measure. And so, as many of you have probably thought about, the concept of biodiversity, that's a common metric in ecology, really trying to understand how many species, of what kind, and how evenly distributed these species are within a community. So the three specific things we're going to be looking at are abundance. So this is the population size of each species. So a household owns a particular species like a cell phone, they may own 3 of them, so the abundance would be 3. Richness is a simple count of how many different species are present. So if a household owns a television, a VCR, and a cell phone, the richness is 3. And then evenness refers to how evenly the species are distributed. So a household owning 3 cell phones and 1 TV is not very evenly distributed, where a household owning 1 of each would be perfectly even. So these are the ecological metrics that we're trying to account for using a number of ecological tools, and I should mention as well, we calculate a number of these using a software called Primer-E. Now, to feed into this approach and into these characterization of our community, we're getting our product data from a number of sources. We're primarily looking at the Consumer Electronics Association annual survey, but we're also looking at sales and lifespan data reported in the US EPA e-waste assessment. We're doing some of our own material flow analysis modeling and looking for statistics about these products wherever we can find them in both the technical literature as well as industry literature, and that result reported by consultants. So thinking about some of these results, I'm first going to show you what we see when we think about abundance. So I have two graphs on the screen. The top one focuses on what we would call stationary products, those that you don't carry around with you that stay in your house. The bottom one focusing on mobile products, so those that you have the ability to take and go, like an e-reader or a cell phone. Now the x-axis shows the years, and the y-axis shows the size or abundance of individuals within each of the species population. So looking at the top one, for example, in 1990, an average U.S. household owned a little less than 2 compact cathode ray tube or CRT TVs, whereas in 2010 they owned an average of 3. If you look at this over the course of the lifespan in terms of the products being owned at different times, you see some really interesting trends. Particularly if you look at the stationary subset, a number of those peaked very early and then have begun to taper off or to decline. So we actually see the CRT TVs declining. We see the CRT monitors declining as well, and then we see some of these leveling off, like BCR or desktop computers. Where much of the rapid growth in the mobile category is happening, we're in the categories of cell phone, cameras, and now smartphones. And these products are all growing. We can also look at this in terms of figuring out the richness, where we see 8 species in 1990, 15 10 years later, and now we have an average of about 20 species present in the average U.S. household. So these are not surprising trends. We know that we're consuming more and more products, but it is very interesting to look at where some of the inflection points and where some of the rapid changes are happening. Then we might start to ask additional questions. So are we actually getting something out of these additional products? Do we get, as consumers, more functions? Or are we simply buying more products? We look at, to answer these type of questions, we begin to try to define what these functions are. And this has not been an easy task. In fact, it's been one of the more challenging exercises so far, is to delineate functions into categories. Our approach thus far has been to define primary functions, again those being the reasons why you bought the products, into 5 categories: audiovisual playing, audiovisual recording, data transfer, hard copy interface, and voice communication. And you can see some representative products surrounding each of those. We also then begin to see some of the secondary function. Now we don't associate those only with certain primary functions. They actually span many of the functions, so there's sort of a spectrum. So you might see anything from web browsing to GPS, to playing videos, to organizing data. There's a number of different secondary functions that are available to consumers. So then we want to start seeing how these trends have changed over time. So what I'm showing on this next graph, and it may take a moment for this to kind of sink in the upper left-hand corner, we're showing a graph over this 10-year period that shows the number of products owned in each of the functional groups. So, for example, using the legend on the left-hand corner, you'll see that we have gone from, in the early 90s, owning about 3 products that provide us the function of audiovisual playback, to now in 2010 and more recently about 10 products. So those include anything from your television and DVD, VCR, to your cell phone, tablet, e-reader, etc. So we have seen an enormous growth in the ownership of products in that particular functional group. We've seen similar growth, although not exaggerated, in all the remaining categories. And again, this is in the number of products owned. What's interesting, though, is when you look at the bottom right graph and we look at the total number of functions provided. So not the primary functions now, but the secondary functions. So how many different things can I do with these products? And what you see here is that there's actually some different categories that begin to emerge. Most of the functionality gains have in fact been in products that are related to voice communication, so cell phones and smartphones, as well as those related to AV playback, not surprising, and data transfer, so the computers, laptops, etc. What's very interesting is that although there's a general trend of increasing, these increases have happened rather sporadically. So we see some stepwise increases. So for example, we've gone from having about 5 functions that a typical data transfer or computer type product would provide. There's a jump to about 8, another jump to 9, to 11, etc. So we see some periods of innovation that happen every few years, or some cycles of innovation in these products that now give new functionality. For example, a cell phone, or in this light blue starred category, might have been used for talking, and later for texting, for camera, for image capture, etc., and then emailing, and then GPS, etc. So you see these functions evolve over time. So this becomes very interesting to us from a sustainability perspective. How could you potentially provide the functions that people want with less products? So this idea of dematerialization. So then we tried to map out some of the secondary functions a little bit further. What are the ones that we really are getting a lot of functionality? Now, this particular radar graph shows 3 periods of time from the early 90s through 2010 in the red in what we're calling weighted functional capacity. So this is the number of functions that are provided multiplied by the actual ownership of those products. So if a phone provided a certain amount of recording video functionality, I might multiply that by 3 phones per household and add it across all of the functional categories. So we see most of this demand for function to be in a few particular categories: recording video, images, viewing images and words like an e-reader, playing video, audio, storing data, web browsing, and Wi-Fi connectivity. So as we begin to try to explore some of these functional capacities that a household is demanding, you can really see where the trends are going. And then we begin to think about, in terms of designers, how could we then begin to dematerialize our products, so fewer products, but very, very functional products. So looking instead, one thing that this perspective allows us to do is take the emphasis off a per product sustainability and maybe begin thinking about a per function sustainability. And then we can begin to think about replacing products that have redundant functions. Does a community need 10 products that provide the same function? Now that's a very tricky question, because then we're starting to bring in some behavior components. And I'll speak in a few moments about some next steps to address that. So then the question, though, really becomes is, we're buying more products, we're also getting more functionality per product. What does this mean in terms of sustainability, in terms of our energy consumed and the materials and waste generated? Really quickly, though, I do want to mention that in terms of getting at some of these functional questions, one of our next steps is to do some consumer surveys. So why do we as consumers purchase some products that have redundant functions, but we're satisfied with others? And we suspect that, that some intuitive factors are at play. For example, a photographer is not going to be satisfied with the functionality of his camera phone on his smartphone, rather, but would want a designated camera for photography. There's other functions that we might accept a lower level of functionality, or a minimum. So we want to know, what is the minimum level of functionality, and why do people buy certain products together or separately? So this is really the next step in this work, is trying to understand the interactions, those plus-minus signs between the products in our community. I want to speak very briefly about some of the other work that we have going on that relates to this. So once we know what this community of products looks like, how can we then begin applying some of our sustainability assessments to measure the sustainability, say the embodied energy or the energy flows for the community, rather than the products? So I'll speak really briefly about this approach. What we're doing in this area is a hybrid life cycle assessment of the entire community of consumer electronics. And when I say hybrid LCA, what we're doing is we're combining an economic input-output LCA, which gives an aggregate, very average supply chain environmental impact for all of the materials contained in the computer, all of the product manufacturing steps, and all of the upstream processes to get that computer from raw materials to a consumer's door. We're doing this with data and with the model generated by Carnegie Mellon and their EIO LCA model. And to parameterize this model, you need prices, because this is based on the flows of materials and energy through different economic sectors in the United States. And those prices we're getting from Consumer Reports and other average industry data. One challenge to this is that this model follows along with the United States economic input-output tables that are only released on a 5-year period, every 5 years, and there's about a 5-year lag. So right now in 2012, we're still waiting to process the 2007 EIO data. So we're behind a bit, and there's some work that needs to be done to bring this up. So keep that in mind as you view the results. Now, hybrid means that we're combining this EIO LCA with what we call process-based LCA. And this is the traditional type of life cycle assessment many of you are probably familiar with, in which we're looking at the environmental impacts associated with getting the energy that it takes to run these computers once they're in the home, so the use phase. And this we're collecting much of this data from literature, from product labeling efforts like Energy Star, but as well as actually directly measuring, say, plug it into the wall and measure the power consumed with a kilowatt under different operation modes and time of use. So what I'm going to show next is the first chart here is the life cycle assessment, or the life cycle energy particularly, all of the energy that it takes to make and use a community of electronic products in the U.S. in 1992, 1997, and 2002. And again, recall that there's a lag in the data, so we don't have up-to-date data, and of course this will change. And what this basically means is this is on a per-product basis. This assumes that every household in the U.S. owns one of each of the products that are available at the time. So obviously they don't own the e-readers in 1992. That is 0. And this is the traditional way of looking at LCA and products. So this would tell us a few things. One, hey, this is great. Our environmental impact on a per product basis is going down significantly over time, which is a wonderful a testament to the efforts that have put in place in terms of greening our manufacturing processes, our supply chain, and our energy efficiency. It also shows us that the areas of prioritization really would be in the desktop computer, which we own a number of during that time period, and it's also very energy intensive to make, and the laptop computer, followed only moderately by, say, a CRT TV, and perhaps the VCR. And again, not that a VCR is necessarily as environmentally intensive as a computer, but it's one of the products that's there at the time. Okay, so this tells one story. Now we want to look at what the environmental impact would be if instead you looked at the community based on what we actually own, rather than just adding up all the potential products that are out there. So the next result that I'm showing is the embodied energy per household or per community. So this takes into account the actual ownership rate of the products. And what we in fact see is two very surprising facts. One being that the increased consumption of products over this time period is actually offsetting and rebounding against the efficiency gains over time. So as a community of products, we're doing worse. It's great that we've got efficiency gains, but they can't keep pace with increased consumption. The other thing that's very interesting is products that you may not expect actually begin to be more important. So in this case, the dominant product is a CRT TV, not necessarily because it itself has a higher environmental impact, but only because we own so many of them. If you recall from one of the earlier the first graph I showed on abundance, over this period of time we own between 2 to 3 of these products. we owned less than 1 or 2 of a desktop and laptop. So the challenge really here is then to think about how to use this information. So instead of prioritizing our effort on, say, computer ownership and things like Energy Star and making individual products greener, we want to look at the whole product. Now we need to really focus on consumption. So this is what we're really talking about in this idea of linking consumption and production. Now obviously this is incomplete. This is a first preliminary result, and we've got a number of steps to still accomplish. We want to look at how these results might be sensitive to the purchase price of these products, how they might be sensitive to assumptions about product lifespan and other parameters. And we also need to add more up-to-date data, including the 2007 benchmark data when it's released and processed, and we've added environmental metrics to it. One of the challenges, though, with this approach is we're always going to be lagging behind in the data since this relies on the economic data. And one of the efforts that we're going to put in place to avoid this is now, instead of looking at the products, looking at the actual materials consumed and the embodied energy of the materials, which we can do for a continuous span of dates all the way from 1990 to 2010 so that our data set will match. That's really another next step in this area. I also want to speak very, very quickly about the final task or final research thrust within this concept of community ecology for products, and that's to do with the material and the waste flows. Trying to understand how the structure and ownership of certain products changes how much waste is generated and what we should do with it. So there's a number of different things that there are potentials here, but one of the areas we've started some initial research is in looking at the different ways of managing this material. For example, in the top right, we see this idea of component reuse, which is enabled by a lot of manual labor, disassembly of electronic components, recovery of valuable components for resale, versus just simply throwing it in a shredder and then extracting the materials that come out. Now, using this idea of community ecology as inspiration, we want to start thinking about this notion of competition. We've got two competing technologies that have different parameters, and we want to know which one is optimal, which one is best for specific products, specific materials, and a specific mix of products. So we suspect that the answer to this question is going to vary depending on which products are in play. Products like a desktop computer are much more easily disassembled and recycled for components as compared to products like a smartphone or here a PDA. So we're going to investigate how this is going to change over time. It also will vary depending on which materials are present. So we're looking at actually disassembling representative products from each representative time period, products that describe the community during that time, and looking at what materials are there and what materials we would hope to gain or recover at end of life, what materials go into the system. So this is another sort of secondarily removed step of the research, but I want to mention it because it again reinforces this idea of using community ecology as a new model for managing these products. So next steps here being to develop the multi-criteria decision analysis model that we're working on for this particular question, and then to start actually assessing which end-of-life strategies are the best for specific products versus for the entire community. So that covers most of the research that I wanted to overview today. Again, much of this is just starting, as preliminary, but I really thought it would be interesting, for those of you all who are doing research and education in consumer electronics, to start thinking about where we might begin to diverge in terms of our results and our approaches if we stop looking at products individually and instead thinking about how they're really consumed, which are in these complex communities of products, which requires us to then begin thinking about human behavior, consumption, and all of the messy things that tie in with those. Now, we don't hope to tackle every single one of those. Would be outside the scope of this 3-year project, but we want to begin thinking about how to develop these methods. And ultimately, some of these methods will be applicable to other systems. For example, when we begin to think about renewable energy, we'll know we won't have only one type of photovoltaics. For example, we'll have a complex mix of different photovoltaics that are on the market at the same time, and we'll want to understand how that mix of products changes the environmental performance of a technology. So the idea being that we can learn about community ecology through this sample, this representative group of products. We can learn a lot about consumer electronics and how to better manage them, and then we can take these models and apply them to other systems. So I want to briefly acknowledge a number of funding sources, including the National Science Foundation grant. My student Erin Ryan, who I show here, has been the primary student researcher on this effort, and she's also received financial support from the EPA STAR Fellowship Program for graduate students. And I have a number of wonderful collaborators that span biology and ecology, and my collaborator Christy Tyler, Eric Williams, who many of you all in the electronics community know for his work on LCA and e-waste, and some additional collaborators here at RET, Gabrielle Gaustad and Barbara Casolitis. So that concludes what I wanted to present on today. I'd really love to, like I said, to discuss and talk about this further. There's a lot of potentially interesting applications and questions here. I always love to hear feedback, but I'm also interested in other topics as well. And if other things come up, for example, as I mentioned, sustainability, education, etc., would love to talk about those as well.
Thank you very much, Callie. We'll take some questions from the audience here. I'll be repeating those questions so Callie can hear them, and then we'll answer any questions that we've received online. So are there questions from our audience here? And seeing none right now, do we have questions that have been typed in at all?
There aren't any questions at this time.
Okay, I guess we have no other questions. Did you want to talk a little bit about how you're doing some of this sustainability curriculum in some of your coursework there in your department, Kelly?
Sure, and I'll mention really quickly that one of the interesting things, the interesting origins of this particular project came from a course in industrial ecology that I teach here at RET. It's a fascinating subject to me, and for any of you all who might not be familiar with the topic, I think it's a great wealth of ideas. I was discussing the book and teaching the class with my husband, who is also a biologist and ecologist, and he flipped through it and said, it's interesting, they're calling this ecology, but this isn't really what ecologists always think about. There's community ecology, population ecology, a number of other subfields that aren't traditionally represented in the field of industrial ecology, which has really been focused on sort of ecosystem metaphors. So we started brainstorming about new areas and new potential models, and I began assigning to my course in industrial ecology a midterm project for students to find ideas from biology that they might think were really cool or really interested, that hadn't yet been used in industrial ecology, and then bring those back to class and write up a brief proposal or literature review about how you could potentially adapt these biological concepts into industrial ecology models. And my student Erin, who I mentioned here, this was actually one of the topics that she explored. And so this project from the course actually turned into this major research effort here. And this was both exciting for me as a faculty, getting to really do some very use-inspired projects, but it also really represents the type of our curricular approach here. Very problem-based and very research-oriented. So many of the students in our program going through the different courses that we offer integrate their research into the courses. The projects that they do in the courses has some relevance back to their research. So they're spending a lot of time thinking about how the research and the coursework intersect, which obviously makes a great use of their time, but also really we found supplements their research well. So the students who are coming through the program, for example, our first graduate did a good bit of research around the topic of organic photovoltaics. but became very interested in life cycle assessment through the coursework that she took. And so her dissertation ultimately included both of those perspectives. And what we hope to graduate here are what we call T-shaped students, students who have a lot of technical expertise, but also a lot of breadth and ability to connect their technical fields to social, environmental, and economic issues of the day.
It sounds very good. We do have a question here now.
With the latest introduction of I-5, there seems to be a phenomenal demand for I-5. In relation to that, that consumer behavior is any different than what has been observed in the past?
Okay, I don't know if you heard the question.
I couldn't hear all of it, no.
Okay, it was on I-5. There's growing interest. Tremendous interest and growth in I-5.
And so how does that compare or contrast with the previous product introductions in terms of impact on youth?
And how does that compare to previous product introductions on for electronics?
Right. What's interesting is that, our data isn't, and that's a great question, and it really gets back to this question of, are people really buying sort of, are they really getting new functionality or something that's better or more products? And, obviously the Apple does a very good job at both of those things. But it is a very interesting question. Now, we haven't yet caught that in our data since we're a couple years behind in terms of when these national statistics come out and can be integrated. So we won't have, say, 2012 consumption data for another year or two. But what is very interesting that this question raises is this idea of sort of functionality and products that can't easily be fit into some of our categories. And one thing I didn't speak of today, but that we're trying to get our heads around, is this idea of emergent functionality. So one product function, as in a number of the Apple products that you see, is you have the ability to have sort of enhanced, say, audiovisual playback due to new technology and the Retina and every display and everything like that. So this is no longer, is that function really comparable to, say, a tablet that doesn't have that technology, or is that functionality better or somehow more valuable to a consumer? So that's one of the things we're going to try to assess in the consumer survey. Another thing this brings about is now this idea of emergent functionality also gets into play where functions begin to combine. So a laptop computer, in the past, we might characterize something like a laptop or a tablet as, computing, but now we have the challenge of saying, well, it's portable computing, and the smaller it gets, the more portable it is. That's, again, there's kind of a gradient in a number of these functions, and dividing up when it becomes something new versus when it's an existing function is challenging. So I think that the Apple product is a great example of that, because it's really got, pushing the limits of what we've previously categorized as functionality, or it's enhancing some of the functionality. How do you categorize that? We haven't figured out yet. That's a great point, a great question. And hopefully we'll, it would be great, and when we actually do get these statistics for 2012, if you actually see any changes in any of the categories.
Okay, we have another question here from our audience.
Hi, Kelly. Can you hear me?
A little.
I am a biologist and ecologist by training, and this isn't really a question. It's more of a sort of vague observation, maybe some things to keep in mind. It's a little bit related to the discussion about the iPhone and consumer choices. You talked a little bit about dematerialization, and it made me think about the concept of planned obsolescence.
Yes.
Which is obviously a big part of electronics manufacturing and electronics marketing. And that's not really something that has a counterpart in nature. Nature doesn't plan for obsolescence. Obviously, the more adaptive organisms are the ones that survive in nature. So that would correspond to what you're talking about, the devices that are more versatile, have more functions. I think something that's going to be important to keep in mind and maybe to explore are concepts from evolution and concepts from consumer psychology and behavior, because you're not really looking at natural selection, you're looking at highly artificial selection.
Yep.
Human consumer factor involved, and it might be worth delving a little bit deeper into marketing campaigns by manufacturers and the reasons why consumers decide to have the products that they do. I think a lot of the times consumers don't even make the choices that they make based on functionality. I think
Right.
sometimes they don't even know half of the functions that their devices have. I think it's much more about status and prestige and keeping up with their cohorts rather than about functionality. So the selection pressure that we're putting on our products is very different from what would be put on organisms in a real community. And that's just something that occurred to me.
Yeah, that's a great question, and I didn't actually mention any of this today because I was sort of what I was focusing on today was sort of the topics under what we would, the community ecology stuff. But we actually have an interesting collaboration here with the faculty in industrial design where we're looking at emotional attachment to products, and we've been thinking a lot about how to sort of make some analogs between this idea of emotional attachment, emotional response to form, fit, and function of the products, and different, like you mentioned, the sexual selection and the selective pressure on the product. So there's, this is one of the great things about this field is I think that because we haven't traditionally approached industrial ecology this way, there's a huge wealth of topics that we can sort of steal from or borrow respectfully, and to some the extent possible from the broader ecological community. And you raise a great point. Again, I alluded to trying to do the consumer survey, but even that's only going to touch the tip of the iceberg, and there's a huge amount of other mechanisms at play. But one of the interesting things that we're exploring is how to look at analogs between sexual selection and emotional design in products. You raised another good point previously, though, about where the analogy doesn't work. And that's another interesting thing that we're exploring is what about these two comparable or, analogous systems, the natural and the industrial, what about those things are similar? And what aren't? Where does the metaphor break down? And so one of the interesting things you may have noticed, when we're showing sort of the change in the amount of functions over time, is that's a very, on an evolutionary time scale, these changes are happening very quickly. And traditionally you don't have your product, in an ecological system, you may not have organisms evolving so rapidly into having new functions or evolving into new niches or niches changing so quickly. So the fact that we're working at a much different time scale really changes this. So one of what we're doing is looking for comparable ecological analogs to see what we have in similarity. So when we actually look at some of our diversity metrics, which I didn't show a whole lot of today, it's actually very similar to in terms of diversity in an ecological community that's undergoing succession. However, you often see trends of evolution from, invasive species that are more generalist to specialized species in particular niches, and we almost have the opposite trend. We have products evolving from specialist to generalist. So there are some places where the metaphor makes sense and some places where it doesn't, and that's, I think, equally as important to talk about what works and what doesn't. So great points.
Okay, we have a couple questions from our online listeners.
What do you think about the possibilities of using biodegradable materials in the mainstream electronics industry in the near future?
That's a great question, and this is one that we talk about a lot in, I teach a sustainable product design class here with Alex Lobos, who I think many of you all from Illinois remember from his work there. And one of the topics that our students are very interested in when we talk about redesigning electronics is how to integrate bio-based products and biodegradable materials. I think the challenge here, and again this gets back to what we're trying to at least teach in the sustainability curriculum, is to think about the entire system. So I think that the bio-based materials certainly represent an important and exciting transitional technology when we're thinking about moving away from fossil-based products to bio-based products or biodegradable. But the challenge is how it affects the whole, being able to model how it affects the whole system. How do these products fit into our existing recycling infrastructure? Are they actually managed in a way that we can take the most advantage of the biodegradability? How, from a carbon footprint standpoint, do they compare? They're not necessarily fossil-based, but that doesn't mean they're free of emissions, particularly if they're originating from bio-based products that change land use or things like that. So, it's certainly not an area that I'm an expert in, but I think that we don't have all the answers yet in terms of the systemic impacts to really know if they're going to be a long-term solution or more of a transitional technology. But they may even have value even if there is not, getting back to sort of the psychology of it, they may have value even in consciousness raising, even if they don't turn out to be a huge net benefit in terms of sustainability. But ultimately, I think any of these solutions are moving in the right direction, but we also have to think about consumption, because the per product solutions won't be enough to make a huge net impact.
Okay, there's one other question.
Are you interested in just IT and telecommunication products, or will you look at other electrical equipment?
Oh, that's a great question, and we have a number of people, say you're not including everything. So we talked to someone from Texas Instruments, says you don't have a calculator in there, or what about household appliances or things like that. Our particular focus for this project is consumer electronics at a household level. But one of the things that really fascinates me is how you could possibly extend this to look at appliances in general, and how you could potentially extend it to look at other electronic, any product with a plug. We're not doing that just simply because, bandwidth issues, but I believe that the benefit of this particular approach is with appropriate adaptation or modification, it could include those. And obviously from the perspective of e-waste and the ideal would be to include every product with a plug, although I don't think in our scope we're going to be able to get to those.
Okay, do we have any further questions? Okay, with that then, we'd like to thank you, Callie, for being with us today, and we'll be talking with you again soon. Thank you.
Great. Thank you so much for having me. I really enjoyed speaking with you all.
Okay, and thank you to everyone having here to watch the